our journey today. I will now try to explain how the matrices can be understood as linear mappings, what it means linear, and how to approach the matrix calculus so that we really can compute the solutions effectively. At least the first steps towards that. So, if we imagine we have got a matrix, I will just write it like this. So there will be A1, 1, and all the other ones, and I don't care whether it's 2 by 2 matrix or 2 million by 2 million. It's just the matter of size of our data, right? And here we have got a unknown vector of coordinates. So it will be this way, and we want to prescribe the value, right? B1, Bn. That's the linear equation. But we can view it in such a way that we just write A times X equals B. Times meet the matrix multiplication. So we have got big matrix, one column. So the result is one column of the same size. Yes, so here should be M. Sorry for that, because we have M equations. So N is the number of columns here, right? So this is N, and this is M. Right, so this is our size. And so we can understand this in such a way that we simply have the matrix A, and we take X, and we map it to A times X, which I will call Y. So this guy is in, say, if we are in reals, it would be Rn, but let us consider general scalars, Kn, and this guy will be in Km, and Y is simply only the letter we use for the value, right? And the solution of the equation means that we are seeking for x's where the mapping, so let's call it phi, where phi maps some yet unknown x to the given value b, right? And this is the way how we can understand matrices as mappings. And we shall see that it will also work the other way around in a more abstract way, but for today, let's stick to this picture. And now we want to be able to solve these equations. So what does it mean? So we can do operations with the left-hand side, which will be done at the same time with the right-hand side and will not change the result at all. So the easiest way is if we seek for the x's, which would give 0. So that's the so-called homogeneous system of equations. And in this case, we can do whatever we want with the left-hand side, and it won't change the right-hand side. And that's what we call the equivalent operations with matrices. So this is here. So let's look at this here. So what can we do? So if we don't want to change the solutions, we can perform reasonable operations with the rows, right? We can interchange the rows, doesn't change the solutions at all. We can multiply any row with a non-zero scalar, so we will expect that our scalars are at least the integral domains, so like integers are, right? So non-zero scalar means that a multiple by this non-zero scalar will again be non-zero. So if we are in a field of scalars, so for simplification, you can simply assume that we are over reals or over complex numbers, then it's reversible, right? So it's invertible scalar. So the best way would be just, we would say we want to multiply a row with a invertible scalar. That's more safe. And we can also add another row to some of those other given ones, right? So that's again something which will not change the solutions. And this is called the elementary row transformations. We can also do the same with elementary column transformations. And here you have an algorithm. I will not explain in detail, but it's described step by step here, and you will see it also in the left-hand column, and practically done in great detail, how to eliminate step by step the rows so that finally you get to what we call the row echelon form. And the row echelon form is done in such a way that, for example, if you have a matrix, it will be 1, 1, 2, 3, and so on, and the second line would be also 1, 1, 2, 3, and so on, and it will go further. So I can do the change in such a way that I replace the second line, I copy the first one and replace the second one, so that I subtract the first one from the second. So it will be 0, -1, and so on, right? And you see what I achieved is I got the 0 here. I will do the same with all the other rows, and that will be giving me a column of zeros except of the very first one, and the first one is nice here, and it's called the pivot for the procedure. And this way we can simply go on, and finally we get what's called a row echelon form, which would be something like this, and here will be everywhere 0, right? Zeros, and maybe some last lines will be zeros too, right? So this is the goal to achieve, because then, of course, if we want to deal with such a matrix, and we have this equality, and of course whatever we did with these rows before is now done also with the column here in the beginning, right? But if it's looking in the end like this, so if in the column B here in the bottom slope would be something which is not 0, then the whole system did not have any solution, which, coming back to this picture, means that simply the right hand side B, which we prescribed, simply doesn't sit in the image, because here we can look at all the values we can achieve. That's called the image in the mapping given by the matrix A. And if we prescribe something which is not hit by the image, then we can't solve the system. That's so simple. And this happens in the row echelon form, it happens this way, right? And then if this doesn't not happen, so if this is 0, then of course we can fix all these columns as those where we put in some free parameters, and we then choose solutions which would be something like 1 for these columns, right? And clearly, I mean, if this is M and this is N, so you see there can't be more than what's available. So we can simply we can always prescribe the parameters so that you have got 1 here and zeros everywhere else for the solution, and then you compute what will be here before by going backwards in the elimination row echelon form, right? And you can read through and find out how to get the solution this way very easily. And this is the difference. If you remember, I claimed that it doesn't matter whether you imagine you work with matrices 2 by 2 or 2 million times 2 million, except the efficiency of the steps will not be the same, right? So if it's 2 by 2, so we don't have to care, we can make the substitution as I taught in the beginning of the last video, and we get the result. If we are at the millions of rows and columns, then there is a big problem how to do this efficiently, whereas this computation of the row echelon form is easy. And moreover, you can be more efficient, because you see, once you are there, you can also just use the same trick, and with the non-zero pivots here, you can backwards do the same and get the zeros everywhere above them, right? So that will be also zeros. And then it's even easier how to compute, because then you simply directly compute what are the solutions. And now a big miracle happens, because if I come back, well, it's not a miracle, it's just a simple observation. If I know that my mapping I'm dealing with phi simply takes x, that's the big column of millions of items if we want, and we map it to A times x, then by the basic properties I already pointed out in the previous presentation. So if I take x plus y, two vectors, and map them A times x plus y, then what I get is ax plus ay. So if this is 0, this is also 0, then the sum is 0 as well. So you see that what we call a kernel of the mapping, so the elements, the vectors which are sent to 0, then it's seen that it's closed with respect to addition. If I take c times x, then I map it to a times c times x, and again by associativity this is c times ax, and so again if this was 0, then this is also 0. So you see that actually the kernel, the set of all the elements which satisfy the equation a times x is 0, is closed with respect to the multiplication by constants and also with respect to addition. So it's a vector space by itself in our understanding. But if we have one special solution, so that a times y is b, then a times x plus y will be 0 for the x plus b, so it will be again b. So you see that we can pick up one particular solution, y, and add all the kernel, and you will get again all the solutions, right? So that's the general thing. So the Gauss elimination I already more or less indicated. And now a very, very important point is that actually all the elementary transformations which are used in the elimination, so interchange of the exchanging the rows, is given by multiplying our matrix A from the left by this very matrix, right? You see, so and at this line I simply read what was in the J's position in all the columns. So I actually, in the result, I copy at this position, I copy the J's line, J's row of the A, and the same here, on the J's position, the J's row, I copy the I's one. So that's the exchange. Similarly, this means I multiply the I's row by the scalar A, and here I add in the J's row, I add the I's and J together, right? So you see all the element transformations can be done this way. And so what we did, and we can do exactly the same with the columns, right? So if we make the same elementary transformation but column wise instead of row wise, we get again the same. And if we combine these things together, so the result is that we simply always can find some matrices P and Q. And I told you already what an invertible matrix is. And talking about invertible matrices, it's clear that a multiple of two invertible matrices is again invertible, because if you have A times B, then its inverse is easily written as B inverse times A inverse, right? Because you see, if I write A and B here in the product, then first these two will give E, and then I have B inverse matching B, which is again E, right? So altogether I get, as requested, E from the whole lot of this, right? Right, so therefore, if I do, and we saw that all the elementary transformations are invertible. So if I do them one by one, so finally I multiply all the matrices from the left, which correspond to the elementary row transformations, and all those from the right, which correspond to the column elementary transformation. And in general, I get some unit matrix here in the left upper corner, and the number of the elements of the ones here is independent. Well, I will not give you the proof in this motivating presentation, but you can read through. Those who want to, and those who want to believe and use the tool, just believe and trust us. The number of ones achieved this way does not depend on how we did the eliminations. And this is called the rank of the matrix A. Right? And in the terms of solutions of the equations, so the rank of the A tells us how big the image could be. So you may find so many independent elements, so the right hand sides, which you can't get by summing and multiplying by scalars. We shall call it linear combinations by this. And so you see, this is what we then call the number of the linearly independent rows, and the claim is that the number of the linearly independent rows is the same as the number of the linearly independent columns. This will be coming back many times, and please just give it some care and go through the solved tasks or read the theory or do both, but definitely just pay attention to understand this bit, right? And the last thing I want to tell in this presentation is that actually we have found a way how to compute the inverses by our explanation now, because what we can do is you simply have the matrix A, and you've got, and next to it I will write the matrix E. That's the unit matrix, right? So all the ones on the diagonal, zero elsewhere. And now I put this into the row echelon form. So A will be what I write in the text as matrices of size n and square matrices over scalars, right? So let's think the scalars will be a field of scalars for us now, and we shall run the Gauss elimination and get it to the row echelon form. And so this more elegant with the zeros up as well, right? So what we get was that you get to some A tilde, and here will be some E tilde, and the A tilde is in the row echelon form. And so what we then can look at is the last row. If the last row happens to be 0, then the inverse matrix can't exist, because it means that we just see that the image of the mapping given by A is not the whole Kn. And so the inverse can't be defined, so it can't exist, right? So it can't work. So if it's non-zero, then it means that there is some non-zero element in the right hand bottom here, and then we can move it into, say, I will write then we can make it into E. That's exactly what happens if we put it in this so-called reduced row echelon form. In Sage you have nice method for that, so there is a procedure, and here what you get, and what will appear is the A minus 1. So by hand, simply by doing all the Gaussian elimination, you get up to there. In the computer, this is the way how the A inverse would be computed. You simply reduce the mapping, the original one, to the reduced row echelon form, and do the same operations with E, and what you get is the inverse. So this is not that easy to verify and understand. You would have to think a bit about, please do, but it's definitely easy to remember, and it works. Of course, I mean, who cares, right? Because you can just get A and you write simply A hat minus 1 in Sage, and you get the inverse, or you get the message that it doesn't exist, right? So, but we are now wanting to understand it a little bit, so why not to go through in more detail. So it's all described here, and in the end you see it takes some effort, and we have got these steaming heads here, etc. How to prove things, and here is what I already explained, the matrices as mappings, and that's it. So this was enough for this part of our week.